Classical computers are slow and dumb, incredibly dumb. Me, Orange. Computer 1111110110011000000000. Out of all the letters and digits in the world, computers can only read two zeros and ones. Let's call these two numbers states. Okay, a computer can read strings composed of two states, such as the color orange. This means a system has 2 to the power of n possible configurations. Another notable fact about classical computers is that engineers try to implement computations on smaller base elements, such as transistors. This allows less energy, smaller inertia so that states can switch faster, and we can pack more elements into one device. But this still poses a limit. The limit is that there is still a limit of the computational power. If we want to grow our computer power, our computation must be even smaller than an atom. Welcome to quantum computing, in a nutshell. So here are 2 things you need to know about how quantum computers are different than classical computers: superposition and entanglement. But firstly, we have to get one fact right. Classical computers use bits, but quantum computers use qubits. As mentioned before, bits can be in 2 states only, 0 or 1, but qubits can be both. Qubits can be photons, atoms, electrons, molecules, or something else small enough to render information into a computer. Its 2 states are spin up and spin down. However, because of superposition, a qubit state can be both. Let's take a look at this diagram. Let's annotate the 0 as spin up and 1 as spin down. The red line represents the actual state of the qubit, and as it is more towards the 0, we can measure it as spin up. When I say measure, this is because qubits lie on a magnetic field. When they are at their lowest energy, qubits are spin down, which is equivalent to the opposite direction of the magnetic field. In the case of the diagram, by applying more energy, the red line becomes spin up, which is essentially why we define it as spin up. In this case, the qubit has exited superposition. So yeah, we can control the state of the qubits by the amount of energy we apply, meaning that quantum computers can complete specialized tasks that classical computers cannot. But when we do measure the state of a qubit, well, we have to take into account another quantum phenomenon: entanglement. This describes the behavior of qubits since entangled qubits behave together. Entanglement occurs when 2 qubits interact physically. To achieve this, an example is that a laser beam is fired through a certain type of crystal and causes individual particles to be split into pairs of entangled particles. This is something that we cannot see in the classical world. Einstein called this spooky action at a distance, because it seemed like information was being performed between particles faster than the speed of light. For example, if you try to measure the direction of the spin for a qubit and its spin is spin up, its entanglement qubit will be spin down, no matter how far away it is. This means you can perform deterministic and not random computations. So we can use entanglement for communication, as one qubit will behave in such a way that is predictable in another qubit elsewhere. Wonder how only 300 qubits could map out all the information in the universe starting from the Big Bang? That's how! Let's put this into context. In simple terms, quantum computers use a fundamentally different instruction set than classical computers. A classical input is processed into a quantum state, a superposition of an exponential number of classical states, which we can measure to get a solution. This is an example of a quantum algorithm, but we won't get into that. A popular theoretical use for quantum computers is optimization. In other words, finding the best solution for a problem. For example, you want to invite 10 people to dinner. How many configurations of those 10 people can you have around a dinner table? The answer is 10 factorial. That's around 3.6 million possible configurations. Every time we add a guest to that table, the possible configurations increase exponentially. Classical computers are just not strong enough to calculate for such a large number. However, quantum computers can. With quantum computing, you double the power by adding 1 more qubit. So an 8-qubit quantum computer is double the amount of power of a 7-qubit quantum computer. If you want to double the power of a classical computer, you have to double the amount of total bits. So 256 bits are double the power of 128 bits. In this way, quantum computers are much more efficient. Quantum computers are not going to take over classical computers. No, because there are some cases in which both pose an equal efficiency. But for certain tasks where classical computers cannot perform, as with the example of optimization, quantum computers are the answer.